This is our second lesson on differentiability. The first lesson was a general overview and talked about what graphs look like when they are differentiable versus not differentiable. In this lesson, we'll be talking about more calculus specifics around differentiability. At the beginning of our unit on derivatives, we learned about the formal definition of the derivative. Specifically, one of the definitions that we learned for finding the derivative at a specific point was that f prime of c is equal to the limit as x approaches c of f of x minus f of c all over x minus c. We're going to use that definition now as we think about the derivative at a specific point, because a function is differentiable at a point c if you can take the derivative there. So a reminder about limits: when we take a limit, we know that the limit exists only if the limit exists from the left and from the right, and those two limits are equal. So we're going to have to think about that as we consider differentiability. In terms of notation, as we're looking at derivatives from the left and from the right, we are going to use this notation. F prime, you can see this negative symbol, that means from the left. And then here, F prime, use that plus symbol to show that you're taking the derivative from the right-hand side. So when we're looking at this limit here from the left, this is the definition of the derivative as you approach c from the left. That goes with this one, that notation, f prime from the left. And then as we look at this one, the limit as x approaches c from the right, that's looking at the right-hand derivative. In order to be differentiable, you have to be able to take the derivative, but your function also must be continuous. So thinking back to our definition of continuity in calculus, remember f of c has to exist. The limit as x approaches c of f of x has to exist, so it has to be the same from the left and the right, and f of c and the limit of f of x as x approaches c must be equal. This is actually the first part we'll consider when we're looking at differentiability. If a function isn't continuous, then it is not differentiable. If it is continuous, then the second thing you do is test whether you can take the derivative at that specific point. Okay, so what kind of features make a function not differentiable? So again, we will consider continuity first. For this first graph, you'll actually have to draw this in. There should be a hole here at 2, -1. So this is a rational function actually that has a hole in it at x equals 2. So is this graph differentiable at x equals 2 when there is a hole? The answer is no. And why? Sorry, we don't need to put the no there. What kind of feature makes the function not differentiable? A hole, because f of x is not continuous at the hole. So in this case, at x equals 2. The next situation we want to consider is vertical asymptotes. If you have a vertical asymptote, I'm going to draw this asymptote in, and this one in as well. Is our graph differentiable at x equals -3 and x equals +3? No, because f of x is not continuous. And going back to our specific definition of continuity up here, for situation 1, we can say f of 2 does not exist. So that's where it fails the continuity test. F of 2 does not exist. Over in situation 2, it is the same thing. F of -3 and f of +3 don't exist. and that's why it's not continuous. So thinking about the formal definitions here, the parts in purple are explanations from the formal definitions of continuity about why this function is not differentiable. All right, the next situation we want to think about is a jump or break in the graph. Okay, so here we've got this example. You can see we have two different pieces in this piecewise function. So why is this not continuous? It's not differentiable because it's not continuous. It's not continuous because, and I'm abbreviating here for continuity, not continuous because the limit as x approaches 1 of f of x, and we're approaching from the left here, is not equal to the limit as x approaches 1 from the right. So the overall limit at x equals 1 does not exist because we're approaching two different numbers from the left and the right. Okay, so what do we notice about all these functions? What can we conclude? If a function is not continuous, at x equals c, then it is not differentiable. And there are these different reasons we gave for why it's not continuous. And over here in situation 3, I should have said we were looking at x equals 1, because it's differentiable in other parts of the graph, just not at x equals 1. Okay, let's move to the next page. So we just looked at functions being not continuous and therefore not being differentiable. Now we're going to look at some continuous graphs and ask ourselves, are they differentiable? If not, why not? So instead of using the definition of continuity like we did in the previous examples, this time we're going to use the definition of a derivative to make our conclusion. So in this situation number 4, we're going to think about the derivative from the left. If we're looking at this left part of the graph, so our x value here that we're considering is 2. So looking at the derivative on the left, the derivative, remember, is the same thing as the slope. The slope on the left, so I'm marking f prime of x, and then I'm going to put a little negative symbol down here to show that it's the left-hand side we're thinking, is equal to -1. The slope here, you can see, is -1. Then let's look at the right-hand side. The derivative on the right-hand side equals +1. Since these limits are not the same, since the derivative from the left and the derivative from the right are not the same, this function is not differentiable at 2. So we can say not differentiable at x equals 2. Because the derivative at 2 doesn't exist. It has these two different limits. If the limits are not the same, the overall limit does not exist here. So the limit as the definition of the derivative doesn't exist there. That's why sharp turns don't have derivatives. The other way you can think about this, in our previous lesson or video, we looked at when you zoom in on a function. If it is differentiable at a specific point, it will look like a line at that point. It will look linear because it resembles its tangent line. If we were to zoom in here, it would not look linear no matter how far we zoomed in. Okay, let's look at situation 5, graphs with vertical tangent lines. So we can see here that at x equals 0, the cube root function, or x to the 1/3, the tangent line would be a vertical line. Since the derivative represents the slope at a given point on a function, if the slope of the tangent line is undefined, that means the derivative is also undefined. So you can just think of like this derivative doesn't exist because it's undefined. Okay. Next, let's look at cusps, situation 6. So this is a similar situation if we're thinking about the derivative as the slope of a tangent line. If we're drawing tangent lines along here, they get more and more vertical until you get to this point at x equals 0 where your tangent lines actually do become vertical. If you zoomed in, you would have a vertical tangent line here. Since the tangent line is vertical, that means that the slope is undefined. And if the slope is undefined, that means that the derivative also is undefined or does not exist. If you were to use the formal limit definition of a derivative, you would end up with something like 1 over 0, which we know means that the limit does not exist. So we can say f prime of x here. dne does not exist, whether you're coming from the left or from the right. So we've now looked at all these different scenarios where the derivatives don't exist, or where the function is not continuous and therefore the function is not differentiable. So what's the relationship between differentiability and continuity? There are a few different ways we can think about this. We can say, let's choose black, if f of x is differentiable, and I'm going to abbreviate there, then f of x is continuous. It's guaranteed. Does this work the other way, though? No. If f of x is continuous, f of x might be differentiable. So it does not guarantee that you will be able to take the derivative. You have to test that out. The third way we want to think about this is if f of x is not continuous, then f of x is not differentiable, as we saw in some of the earlier situations and examples. Okay. Moving on to determining differentiability algebraically. We looked at graphs before. Now we're going to look at determining if a function is differentiable at a specific x value. So there are two parts we have to test here. One, we have to test, is the function continuous? Oh, and this should have been at x equals 3, not x equals 1. So is the function continuous at x equals 3? And if it is it also differentiable? So to test continuity, what we want to think about is the limit as x approaches 3 from the left of f of x. Is that equal to the limit from the right? That would guarantee continuity because f of 3 would exist. It's part of this piece on the right, and it would be equal to the overall limit here if these two parts are equal. So thinking about the limit here, I'm going to plug in x squared for the left, and then 6x minus 9 for the right, and then substitute 3. So we get 3 squared, and 6 times 3 minus 9, 9 equals 9. Alright, so it is continuous at x equals 3. Now let's test, is it differentiable? So the goal here is to see, is f prime from the left equal to f prime from the right? So is the derivative the same from the left as it is from the right? So let's take the left-hand piece, which is x squared. That's 2x. And let's take 6x minus 9 from the right. And that derivative is 6. Okay, well, now we want to be more specific. We need to think about the derivative specifically at 3. So let me actually pull this out here and plug in a 3. Oops. Here we go. Instead of an x, make that a 3. And then, yes, the derivative is the same from the left and the right as x approaches 3. So we can say, yes, f of x is differentiable at x equals 3. Here's a second example. So again, first we're going to test for continuity. The limit as x approaches 1 from the left, and the left-hand piece is the negative 2x squared plus 4. And we want to know, is that the same as the limit from the right? And plug in x squared plus 1 there. And substitute in 1, we get negative 2 times 1 squared plus 4. And plugging in 1 here, 1 squared plus 1. Negative 2 plus 4. We get 2 on the right-hand side. 2 equals 2. So it is continuous. All right, now let's test differentiability. So what is the derivative of f as we approach from the left? Looking at this left-hand piece, we get negative 2 times 2 times x. So 2 minus 1, which we know is negative 4x. Clean that up. Negative 4x. There we go. So as we're approaching 1 from the left, that gives us negative 4. Now let's do the right-hand side. As we approach from the right, we get 2x. And plug in 1, we get 2. Are these equal? No. So f of x is not differentiable at x equals 1. Because the derivatives, as we approach from the left and the right, are different. Alright, one final type of algebraic problem. What values of a and b would make the function f of x differentiable at x equals 3? So in order to make it differentiable, again it has to be both continuous and then differentiable. We're going to use both of those here to solve for a and b. So looking at the differentiability part first, if we're approaching from the left, we get 2x minus a. If we're looking from the right-hand side, we just get 1. Okay, plugging in 3, because that's where we're coming from. And we get 6 minus a. So the right-hand and the left-hand side here should be equal in order for this to be differentiable. So we can set these equal and say, let's put it down here. So step 1, step 2, now we're saying 6 minus a has to equal 1. So subtract 6 from both sides. Negative a equals negative 5, so a is 5. Then for b, we're going to use continuity. So in order for it to be continuous, and we could have done this first instead of the differentiability part, the order for this part doesn't matter. So doing the left-hand side and saying that that should be equal to the right-hand side limit of x plus b. And then we're going to plug 3 into both of these. since the limit is approaching 3. And then solve, we'll get as far as we can for a and b. So we have 9 here plus 2. So we have 11 minus 3a equals 3 plus b. Subtract 3 from both sides, you get 8 minus 3a equals b. So if we had started with this piece, we wouldn't be able to solve. We would have to go to the differentiable part next. We did it in the opposite order. Here it doesn't matter. But we found when we did the differentiable part of this problem that a equals 5. So I'm going to plug 5 in and say that that equals b. So 8 minus 15 equals -7. So that's our b value and our a value. And that's it for looking at differentiability algebraically.